In this last module, devoted to flow visualization, we will focus on the abstraction given by topological models that try and build a complete map of the relationship between different parts in the flow, and therefore try and minimize the need for interactive exploration. As we have seen already in experimental techniques, we can see flow elements moving in space, and then we intuitively try to relate how they connect to each other, and therefore build a mental map of how things evolve. In the process, we end up noticing this kind of coherent bundles of strict lines or streamlines or other features or regions where things are rotating and not escaping a particular cell, which really is a very useful way of abstracting a large region of geometrical models into a unified simple concept. So here, for example, in a more computational case, if we look at the bioelectric flow on the surface of the heart, we can use a traditional line integral convolution approach and have this general sense how things work. Or, as we can see on the right, we can augment it with a set of key points and lines. Those are in fact critical points and specific streamlines that come out of them that divide the space in regions that are in some mathematical sense coherent with each other, and we'll talk about what that means. And that makes it easier to understand the overall trends in the data without spending too much time looking around and using interactive exploration. This is true in a way even more so in the three-dimensional case. We have these kind of bundles of streamline or strict lines, and it's very important to understand which of those, for example, share a common source or a common destination, so that one can abstract a group of them without having to memorize the location of each independently. So in general, building this type of abstraction is very useful to reduce the complexity of the data, both in terms of the concept that we need to appreciate, but also the time we spend looking at different details. And so there is the challenge of deciding what does it mean to convey the important properties in the data. But if we manage to express this idea, certainly we would accomplish the goal of reducing the amount of information and data required to produce useful understanding, and in fact also at the same time improving the reliability of the information that one is conveying. And so one has to kind of grapple with how ambiguous terms are, like salient feature, major features, or feature of interest can be, and therefore often people rely on a very application-specific approach, which can be very effective, but it reduces the ability to develop general tools that can be used across different disciplines. So this is where there is the interest of developing more general definitions, and in particular topology is one of such techniques that allow achieving this by looking at the flow from a purely mathematical perspective, and then delegating to a later stage to the expert in a particular domain to determine what those features mean in terms of application, while they have a particular information content at a purely mathematical idea. The idea is to go after this notion of decomposing the space in units or cells of different time, where the elements, for example, in a particular cell, are considered equivalent to each other, or they have a common trend. Just to be practical, for example, when we have different streamlines, if two streamlines have the same source and the same destination, we could say that they are equivalent to each other. In fact, especially if they are adjacent to each other, we could just bundle them together and visualize just one, or draw the boundary of a cell while all the streamlines have that same common property. And this can lead to a more schematic representation without loss of information. So topology has the power to give this type of representation, also often called rubber sheet geometry. Is the idea that characterize information in your data that is invariant with respect of deformation. Here in the top right we saw the animation where the coffee mug and a donut are considered equivalent shapes, just because under continuous deformation they both have solid annular structures around a particular tunnel, and therefore from a topological perspective they don't differ from each other. So effectively there is a study really of connectivity, not the actual geometry and embedding of the geometry. And so, as I said before, for example, if I study how streamlines in terms of source and destination connect to each other, this would be a reliable way to proceed, so that regions of similarity from a topological point of view can be identified. So this is just a drawing that can give an intuition of the direction that we're going after. So once we have a description of a particular flow, the question is really how can we carefully choose a small set of streamlines and points of interest where that we have to draw to give a sense of how the flow is structured. For example, in this case, there is this particular point, there is a source of flow, and there is an understanding that basically all those streamlines in these particular regions are behaving similar to each other, in the sense that they are all coming from the same source. So we don't need to have a dense drawing on lines similar to the line integral convolution. We can just draw a few as a representation. In fact, we could just draw the boundary. Similar here, we have an interesting location where the flow divert on one side or on the other on here, but on the other it actually comes out of a particular source. And so we can highlight point of interest, where interest is defined, for example, in terms of things merging together, bifurcation, things that are created by source, or things that kind of disappear into a sink. This has been used very effectively both in 2 dimensions and 3 dimensions. And so this is a couple of examples of Luria flow, where we see the leak display overlaid with the topological structure, and in the next few slides we'll see what those topological structures mean. Effectively, you see all those key points, also called critical points, where, for example, this is a saddle, the flow split in this location. There are several sources and destination, and this is a surface embedded in 3D. Similarly, here we have a spiraling structure where the flow goes around and come from a particular source. There is here a saddle where the flow bifurcates on the two sides, and so it really helps both driving the attention into the data in the area where we want to highlight those things, and also, if it's computed precisely, avoids the problem that for something like leak or other techniques could be imprecise or not highlight properly the structures that are important of the data. As often happens, so this is a good addition, a good complement to these other techniques. Again, it's not meant to be a replacement. In 3D, this can be even more useful exactly because of the problems with cluttering and occlusion. And so if one can use maybe a hybrid approach where a leaks along cross-section give a sense of the flow, but then only choosing critical points and specific flow lines coming out of those give a sense of what happens in 3D space without having a picture that is too busy and hard to follow. So let's focus on the steady flow case, so that obviously all those concepts can be extended and generalized. So we can start two-dimension and steady flow. And so there, the question is, how do we characterize what's called limit sets? So particularly in a streamline, we look at where they originate and where they end. So what is their limit? Basically integrating both forward and backward. And so those could be different locations. Typically points, but not necessarily points. We'll see some exception of those. And those describe the behavior and the relationship between the behavior of different local evolution of the flow. So given the vector field V, the critical points that we consider the points of greater interest are the points where the vectors are 0. So paradoxically, maybe one would think about the flow is more interesting when the magnitude of the velocities, for example, is particularly high. The reality is that the location where the vector is 0 are interesting because the angle, so if you think in polar coordinate, we have in length and angle of the vector, the angle loses meaning. And so in the neighborhood, the flow doesn't really have a tangent space, and therefore the flow can evolve in many different ways in its local neighborhood. So it gets really potentially complex. And then the complexity, one can look at the derivative or the Jacobian of the flow itself. And normally we make the assumption that the determinant of the Jacobian is non-zero, so it's what I would call an assumption of simplicity of the flow. And then we will look at the eigenvectors and eigenvalues of the Jacobian at this particular location. So intuitively, though, and we'll look at more in detail about eigenvector and eigenvalues computation, we can then determine locally, given, so the point, and all those points here are critical points of value 0. Depending on the values of the Jacobian, they could have this kind of divergent structure of saddle points. They could have, for example, this repelling spiral structure of flow that comes out of the point. You can have focus, where basically the flow comes out straight out, or flow that goes into a node that is kind of similar to a focus but in a way non-symmetric, to some kind of limit cases where the flow is circulating around the location without neither going in or going out. And so if we characterize properly those critical points and then understand the evolution of interesting streamlines around them, we can build a diagram that is often called the phase diagram or phase portrait of the flow, where the critical points are highlighted, and then the flow lines indicate how the critical points relate to each other. So if there is a center, there is a bundle of streamlines that kind of rotate around the center, while if there is a saddle point, there are two main directions that separate flows on one side and the other. So you have basically four regions of flows that kind of don't mix with each other. And then there could be stable or unstable nodes, or effectively sources and sinks or destinations of the flow itself. Overall, with a relatively small number of strokes, brush strokes, one can give a very detailed and very reliable idea of how the flow evolved. Now, as we said, the critical points are where the vector, for example, velocity vector is 0. And now, if we look at the derivative of that vector, the partial derivatives, we build a matrix called Jacobian into D. That would be a 2x2 matrix, and this kind of give the description of the local behavior in the neighborhood of the critical point. In particular, there are two special vectors called eigenvectors, and then two values called eigenvector values in a 2x2 matrix that are particularly meaningful and are a good descriptor of the local behavior around the field. And now finding those, well, first of all, maybe let's go back in terms of intuition. So the directions here of that separate the regions of coherent flow around the saddle point, those two directions are the directions of the eigenvector. So those are not just mathematical concepts, they have a very concrete meaning once we know how to compute it and attach them to the visualization. Now the question is, how do we compute eigenvectors and eigenvalues? And in low dimension, actually, that's not complicated. But in general, they are the result of solving this particular equation, determinant of A minus lambda I equal to 0, where lambda is the vector of eigenvalues of the matrix A. And this is again is called the characteristic equation of the matrix. Practically, this means that if a vector x satisfies this particular equation for one of the eigenvectors, so A is the matrix, so Ax equal to lambda x, where lambda is an eigenvector of A. So x is a eigenvector of the matrix itself. So I'm preparing. I prepared a little demo. This is from Wolfram Alpha, the online website, to give an intuition of what does it mean that for a matrix A, multiply for a vector is the same as the vector multiplied by the scalar. It's kind of not obvious how that would work. There is a demonstration, and so I have here the information that here we see on this side of the demo the matrix A with 4 values, and those are the value A11, A12, A21, A22. And so I can put a red vector, that would be this one, and here interactively I can move my input vector. And now the blue vector is the result of multiply the vector for the matrix A. And so if we look at the equation, what would that mean to be an eigenvector? That means the multiplication of the vector for the matrix is the same as the multiply the vector by a scalar. In geometrica, what does it mean? So if I find a location where multiply the vectors, like in this case, I multiply the red vector by the matrix, and I get a vector that has the same direction, so it's the same as multiplying the vector by a scalar. So this modulo adjusting for the length. So this is the direction of an eigenvector. So you see that when I move, so this happened really for a particular direction. If I move more, oh, this is happening again for a second direction. And then if I rotate even more, now this is the same direction as before, just on the other side. So it's still the same direction multiplied by the scalar. And then it happens again, but again, this is a repetition on the other side. So one can see how, depending, I'll modify the value of the matrix. So when I multiply the vector by the matrix, I can find two directions by which the multiplication by the matrix is really changing the length of the vector. So now I can, if I change the value of the matrix, this will happen in different values. And so for each matrix, I will find a different eigenvalue or different eigenvector. You see how this is happening in a different way. And in fact, if I go, now I simply change the second term. Notice now that when I, this is interesting because this is a rotation matrix. So if I take this vector and multiply by the array, the blue vector gets rotated in counterclockwise by a small angle. And so now, no matter what red line I choose, it never gets to be aligned with the blue line. What does this mean? This means that this matrix with those coefficients, so you can also see here, does not have real eigenvalues. It has two eigenvalues, but those are have an imaginary component. Those are two complex numbers. And so when the multiplication happens, so this is not a property that is for granted that any matrix that you take, you will have those eigenvectors with that structure. They can be complex numbers and so on. So hopefully this gives a kind of an intuition of the geometric meaning of the eigenvalues and eigenvectors and how they're being used. Practically, those can be computed by the solution of this linear equation, so that, or also called the characteristic equation, so that we can find the actual value. So in a 2D case, for example, we can have a matrix like this, and then we compute the multiplication for A minus, so if you go here, so A minus lambda I is this representation, and then the determinant can be computed now explicitly, and then we obtain, what's interesting is that the solution of this matrix representation give us actually a quadratic equation, and that makes sense because we need to find two eigenvalues, sorry, and and those could be either two real ones, or as we saw in the demo for a rotational matrix, or they could be complex numbers. And as you can see, for example, if the square root has a negative value underneath, this would give an imaginary component, so we would have two complex numbers where they differ only by the imaginary component. So in this case, the eigenvalues are real, and they have values -1 and -2. So then going back to the intuitive meaning, so we know that in principle the eigenvalues they can have real components and imaginary components, either both or only real or only imaginary. And so based on that information we can classify how the flow behaves. For example, if we have what's called a repelling focus, we will have imaginary terms that are not non-zero, and then we have two positive real terms, and then depending whether they are equal to each other or not, this is it's kind of a nice spiral, or it's a little bit modified like this. In a saddle point, the imaginary component are at 0, and then the two real values are one positive and one negative. Here it's described as the product is negative. And so another very interesting case is when you have what's called a center, so a location where around we will have flows that do not either go in or go out. And so in this case we have imaginary values, but both real values are 0. And then the remaining cases are attractive focus instead of repelling focus, and attracting node instead of repelling node. So what's interesting, just computing those 4 numbers, we can actually classify precisely what is the behavior of the flow in the neighborhood. So the visualization can be complemented with precise numerical computation extracted from the data. So intuitively then we see that positive real numbers indicate kind of repulsion from the critical point, and negative refer to attraction. And again, in a saddle there is a things repel along one of the eigenvectors and attract along the other. And then if there are no negative imaginary component, there is some degree of rotation around the critical point. And so this in fact actually is an important aspect, because if the vector field we have is the gradient of the scalar field, then the imaginary components are always 0. And that's kind of what's also called a conservative vector field. If the vector field has some critical point with non-zero imaginary component, that's definitely not a gradient of a scalar field. So the idea then kind of more algorithmically is that one has to first find the critical points. And now here you have to find the points where the all components, 2 components we are in 2D, or 3 components if we're in 3D, of the vector are 0. And so this is kind of similar to computing ISO value, and so we just need to kind of go through the cells, see when it's possible to have zeros in a particular cells, and really the only twist is that we need to find, in a way, concurrent zeros of 2 or 3 scalar fields at the same time, which those will be the components of the vector field. Once we find the critical points, the next step is to classify them so that we can classify the behavior of the flow in the neighborhood of each of those points. So we have seen that computing eigenvalues, eigenvectors is the approach, and in particular just from the eigenvector we can generally understand if something is attracting or repelling. We will need the eigenvectors then to understand in which direction, in which geometric direction the attracting behavior or repelling behavior is happening. And so going back to the idea of having a phase portrait representation, so we can think about having a vector field with a more visual approach. And then, so here we can generally see in which direction the flow is moving, but we don't necessarily have a precise understanding of which critical point is component with which. So once we classify, for example, the critical points, so we can see what are the sources and where are the sinks, so where the flow emerges and where the flow kind of disappear. And so this is based on the idea of limit sets. So we look at every streamline again as an integral, and then if we push the integral to the limit, so technically the endpoints, the source and destination, are not part of the streamline itself, but going to the limit we can see, for example, in this particular streamline, we can see that there is, if we go integrate backward, we'll find the source, this particular point, and if we integrate forward to the limit, the destination is there. And just to give an intuition why I say that the limits are included, again, the limits is where the vector intensity, the vector magnitude is 0. So if you start on the critical point itself and you apply an integration method, since, for example, velocity is 0, I start from this point, every step forward or backward would be multiplied by 0 because that is the vector itself, so one never moves from this point. So every streamline like this should be thought of as an open interval where the flow gets lower and lower and lower, and in principle never gets all the way to the sink or never really start from the source. And you need a kind of a limit operator to get to that point and understand how they relate. So we can look at then classifying entire regions based, for example, having a common sink. So in this case, we see the green region. So we look at a particular, this particular sink. So we look at all the streamlines. They have this the common limit set. So this entire bundle, we could call it a basin, where all the streamline have the same limit set, and they all end up in this particular sink. And so here then we need much less information. We could really get rid of a lot of the lines, since it's clear where things are ending up. In a dual way, we can look at a source and then look at all the, so in a way, in principle, conceptually, we start with all the points in the neighborhood, in the neighborhood of this particular source. And then this is the region of all, this blue regions is the region all the streamlines then emerge from the particular source. By the way, here it's extended a little bit because conceptually some of those lines kind of go out and come back in. And so those gets added from boundary effects. Dealing with boundary effects, it's a little bit tricky but definitely can be done in a consistent way. And then here we see, for example, how a saddle is represented. So here we have this particular critical point, have those main directions, we'll see also again later, and the saddle point partition the flow in the median neighborhood in 4 regions. By the way, one is white, one is blue. Locally, those 2 green areas that they're now grouped because the basing they all go to the same sink, but locally here things are nicely separated from each other. And again, it's all about, when we talk about critical points, is all related to local behaviors. Here we have this particular source is kind of a spiraling source, and so as you remember, that could be so there is a rotational aspect to it, and so there is imaginary components, and then it's a source, so that there is a positive real component of the eigenvectors. A node, so it's kind of similar, so it's also it can be a source or a sink. The only thing is that the 2 real components are not coincident, while, for example, in a focus it's a similar situation, but the 2 real terms are the same. So here we can look in this diagram how things relate to each other. So a saddle has only real components and no imaginary one, so has nicely we can see here they can have nicely the 2 eigenvectors that represent how the flow is split local in space, and so that can be again identified just looking at the terms here. If you look at a spiral, then you have the 2 real components are the same, so the 2 eigen values are on top of each other in this complex plane, meaning they have opposite imaginary terms, same real component. In a node here, since is a sink, you have 2 negative real numbers, no imaginary components, but the 2 real terms are not coincident. And here this focus is a source, so no imaginary term, and the 2 real ones are coincident. And then the kind of the most particular ones is the center, where it's kind of rotation around a particular location. The flow does not go in or out. And those are just 2 purely imaginary terms, no real components, and opposite to each other. So one special case of a critical element that is not really a critical point is that one can have an entire cycle of flow that normally would happen just around a center, but this cycle can act itself as a source over a sink. So one can have a kind of a spiraling flow that ends in this rotational structure, while on the other side there is also a spiraling behavior, and that slowly converge on that structure, and that in the middle creates this particular rotational structure that acts kind of separating the flow from inside and outside. And so those are, I guess, numerically the more difficult to compute, because you cannot just look for critical points of where the vector is 0. You have to actually find interesting cycles into the data. But generally we end up kind of dividing the flow in nice cells like this, and so that kind of give a comprehensive description of the flow, and that I hope shows how, for example, even if we don't show the leak underneath, and in fact even if we reduce the lines, as long by a lot, so we have relatively few lines. As long as we trust that we find all the critical points and potentially the cycles that we just discussed, we would know very reliably where the flow is directed, just don't know exactly in the geometry itself. Now, things are very similar in 3 dimensions. The reason why 3D things don't get too complicated is that there can only be 2 conjugate, so 2 opposite complex numbers. So they have same imaginary term and so opposite, sorry, imaginary term, and so that means and the same real one. And so that means that when you have 3 eigenvectors, because then the matrix now is 3 by 3, at least one is entirely real. So we cannot have 3 complex eigenvalues. There can be 2, there can be 4, but to have 4 you have to be in 4 dimension. So this means that in 3 dimension the flow can always be divided into a flow in a 2-dimensional plane where the analysis that we just did would be the same, and then there is kind of a transversal flow, and that flow in a transversal direction is always real. And so there there you will have flow that either goes in or goes out, but you don't have any rotational component. And that also corresponds to the intuition that in 3 dimension you cannot have a full 3D rotation. At the end, the rotation will always happen around a particular axis. And so if we go to classification, so a node, it could be a source and a sink, is a critical point where the eigenvectors are 3 real numbers. They are positive if it's a source, they are negative if it's a sink, and if they are all equal, then the flow is all symmetrically, basically as if things radiated from a sphere. If they're all 3 the same, if they're distinct, you have this node behavior where some lines are kind of curved instead of going straight into the core of the critical point. So when we look at spiraling, then you will have along the plane here we have the 2 complex numbers. They have the same real component and the opposite imaginary one, so that would show a spiraling structure along the plane. But then the third term, it has to be real, so then you would have either the third component also converging in or diverging out in this way. And so either it's a full sink because all the direction go in, or a sort of a spiraling saddle, because on one side there is flow going in, but then instead of going into the point, then the flow emerge out of the critical point. And then last, in terms of classification, it's a more traditional saddle point where all the eigenvalues are real, but differently from the source node or destination, in general the node, one of the eigenvalues has one sign and the 2 have a different sign, and so either 1 positive and 2 negative, or 1 negative and 2 positive. And so again, modulo all the possible symmetries that represent all the possible configurations in 3 dimensions. And now just to conclude, a couple of the examples that can be shown in 3D. Again, instead of showing all the structure of the flow, one can show the critical points and the boundary of the cells and potentially the surfaces that are around some of those boundaries. And this as you can see, especially actually in 3D, becomes really useful. It's still potentially relatively busy, so one can have additional filtering that has to be applied, but has the potential to show a lot of information in relatively small set of lines. This is another example in 3D. We see all these various cells, and effectively in all those regions, this is a conservative vector field, so it's kind of the gradient of a scalar field. And so, but you see in each of those cells, we know that the flows start from a particular source and then in a particular sinks, and that simplifies the complexity of the visualization because one can reduce the number of streamlines that get visualized. And a last extension or variation of this type of work is the idea of using moving cutting planes for 3 dimensions. So instead of using the full power of the 3D approach, when appropriate, one can look at using trajectories over which we compute the topology on the scalar field, in a 2-dimensional scalar field, and that can also be very revealing of structures in the data. Typically, if they have a certain symmetry or certain axis along things evolve, in which case this can be more informative than a full-blown 3D topology that can also be problematic for occlusion and complexity. So here we can see interesting examples where once we identify, for example, a proper cutting plane, then can be swept through the data, and then we can see the related topological structure for each of those cross section. Same here on the bottom right, and that actually give a kind of cleaner visualization of the data that can nicely complement what we do with a full 3D representation. And as the last one, we see this nice representation of a phenomenon equivalent to this bubble that is created in an experimental setting. And here, again, with a relatively limited number of lines, one can actually exhaustively show the entire vortex breakdown bubbles in this cylindrical container, and give the scientist a full understanding of what's happening in the data. And so with this, I conclude the modules relatively to vector fields. And thank you very much for your attention. And then next week, we'll move on to a new topic.